Here's the free response from the summative assessment on acid-base equilibria. Question 1 gave us 3 solutions, and eventually in part A, we want to write letters of the solutions in the boxes below to rank the solutions in order of increasing pH. Explain your reasoning for the ranking. So if you just put the letters in and randomly you guessed right, you got nothing if you didn't put any kind of an explanation in there. I think it helps to go through these solutions and figure out what kind of particles are present. So in solution A, I know that sodium hydroxide is a strong base, and it's mixed with HNO3, which is nitric acid. And if I wasn't sure, they tell me that the Ka is very large. It is extremely large because nitric acid is a strong acid. So in solution A, I've got strong acid, strong base, and it looks like there's equal volumes of equal molar solutions. So this resulting solution should be 100% neutral with a pH of about 7. Solution B has sodium nitrate. And I know sodium is totally neutral. It obviously doesn't produce hydrogen, and it doesn't react with hydrogen. And nitrate is also neutral. Nitrate is the conjugate base of a strong acid. So even though it's a negative ion and it looks like it could be attracted to hydrogen, in the presence of hydrogen, it just dissociates fully anyways. So the nitrate and sodium together have no effect on the hydrogen concentration, totally neutral. And then we're mixing it with a strong acid. So this is neutral and strong acid. This is just going to be really acidic. And then finally in solution C, we've got HNO2, which is a weak acid, nitrous acid with a Ka that's less than 1, mixed with sodium nitrite, which again, I don't care about the sodium, that's a spectator, but I've got the conjugate basis of a weak acid. This screams buffer, right? I've got equal volumes of equal molar solutions, so I've got that special buffer with a 1-to-1 ratio. So now in ranking these by increasing pH, I want to start with the solution that's the most acidic, and that should be solution B. I've got a neutral solution mixed with a strong acid. The pH should be pretty low. Next comes solution C. This will be an acidic buffer with a 1-to-1 ratio. I know that the pH equals the pKa. They're not asking you to calculate the pH of these solutions, just explain your ranking. But yeah, I mean, without plugging it in a calculator, I could say that the pH should be somewhere around a 4. And then finally, solution A should be totally neutral. Equal volumes of strong acid and strong base, both with the same molarity. Should be 100% neutral with a pH of about 7, which is my highest pH of those 3 options. In part B, the solution that's most resistant to a change in pH, if sodium hydroxide were added, that's got to be my buffer. Solution C. The buffer contains that weak acid. The weak acid, which is the HNO2, can react with the hydroxide. We'll have a hydrogen donor. So we'll be left with the conjugate base, which, yeah, we would get a little bit more of the conjugate base, but that's a weak base. And then I'd be left with water. So as long as the hydroxide is the limiting reactant, we should be able to shift this thing forward, eliminate the hydroxide, and yeah, we'll change these concentrations a little bit. The amount of the original acid will decrease, and the amount of the conjugate base will increase, but I should still have a buffer. And so yeah, the pH might go up a little bit, but not as significantly as I put that in water. I put that in something neutral. If I put that in like with a strong acid, the pH should change quite a bit. Part C, a student is going to make a buffer with a pH of 3.4 using 0.1 molar nitrous acid. And oh, here they actually give me the exact pKa. I estimated around a 4, like 3.4. Ooh, interesting. So we're going to mix that weak acid with strong base sodium hydroxide. Doesn't jump off the paper as being a buffer. Usually I'm thinking that we got to have the weak acid and its conjugate base. But we're going to mix it with some sodium hydroxide strong base. But they're telling me in part 1 that this can result in the formation of a buffer. I just got to explain why and include a net ionic equation. So net ionic, get rid of the spectator ions. Okay, so first let's start with the net ionic equation. The sodium is definitely a spectator ion. The sodium hydroxide, being a strong base, will fully ionize, but the weak acid will not. So I don't get to split apart the sodium nitrate and consider either of those as spectator ions. I mean, this may only ionize by less than 5%. So the acid is the hydrogen donor. We'll get rid of that hydroxide, turn it into water, and we'll be left with a little bit more of the conjugate base. Now, again, make sure that you get rid of the sodium if they ask net ionic, and think too that you cannot ionize something that is not extensively ionized. So only strong electrolytes, which would be strong acids, strong bases, and ionic compounds that are 100% soluble, like our sodium chlorides of the world. The other thing I have to make sure in my equation is that I put in charges by hydroxide. That is an ion, -1 ion, and you got to have that charge in there by the nitrite ion. NO2 without the charge is nitrogen dioxide, which is a toxic brown gas. And I'm pretty sure that's not what we want to form here. We want to form the nitrite ion. So we got to put charges in our net ionic equations for any remaining ions. Now, we kind of mentioned that actually, yeah, we could make a buffer as long as the hydroxide is the limiting reactant. This guy's got to be less than the amount of the original weak acid. So the weak acid can donate the hydrogen. We can form the conjugate base, even though it's not initially present, as long as this drops out. And so then, yeah, it's kind of like this example that I'd written by part B, that if the hydroxide is limiting, that'll decrease down to 0. And yeah, we'll decrease the amount of the weak acid a little bit, and we'll form the conjugate base. So that might start initially at 0, but it can go up in this case, so that, yeah, I can produce a buffer, but I just can't have any hydroxide remaining. If the hydroxide is in excess, then it means that the HNO2 would have been limiting. And if that's limiting, it means that the acid is gone, and I need that to be part of my buffer. Part 2 can be answered with a calculation, but not necessarily necessary. Determine the volume in milliliters of 0.1 molar sodium hydroxide the student should add to 100 milliliters of 0.1 molar HNO2 to make a buffer with a pH of 3.4. Justify with a calculation or an explanation. Which you can do a calculation, or you can kind of think about it. So I want a pH of 3.4, which actually is the pKa. It is the opposite log of the Ka. So then I know that I want that special buffer with a 1-to-1 ratio of acid and base. Okay, so let's see, what are we going to do here? We've got 100 milliliters of that 0.1 molar HNO2. Well, I want this to be equal amounts of HNO2 and nitrite, which maybe from titration talk, you might remember that that would be like the halfway point of a titration. At the halfway point, you've added half as much base as acid, so that the base drops out, the acid goes down by half, and the conjugate base goes up by half. This is kind of like looking at the halfway point in a titration, which then qualitatively we could say, okay, so if I'm starting with 100 milliliters of 0.1 molar HNO2, and the base is also 0.1 molar, I want half as much. I want half the volume. So if I'm starting with 50 milliliters of acid, 100 milliliters of acid, I want 50 milliliters of base. And then it's like the halfway point in the titration, where your acid would go down by half and your conjugate base goes up by half. And again, the hydroxide is limiting, so that's out. You could also do some calculations. You could figure out like how many moles of HNO2 you have. You could kind of look at an ice table to figure out when that would go down by half, how many moles of sodium hydroxide would I need to add. And then if I know that it's a 0.1 molar solution, we could say 0.1 molar sodium hydroxide equals moles per volume, moles per liter. And from there we could solve for the volume. But you didn't necessarily need calculation, but you kind of have to think about like, how do I get to the point where there's a buffer with a 1-to-1 ratio? Yeah, it's like the halfway point in a titration. And then finally, we had a particle model. A new buffer is made using HNO2 as one of the ingredients. A particle representation of a small portion of the buffer is shown below. Cations and water molecules are not shown. Is the pH of the buffer represented in the diagram below greater than, less than, or equal to 3.4? So 3.4 was the 1-to-1 ratio buffer. But now if I look at the composition of this buffer, it looks like there's actually more acid than conjugate base. It's still a buffer. I've still got the weak acid and conjugate base. But if there's more acid in the buffer, then I would expect the pH to be a little bit lower or a little more acidic. Question 2 was a titration. Potassium sorbate is commonly found in diet soft drinks. Somebody made a solution of potassium sorbate. They titrated a 50 milliliter sample of that stock solution with 1.4 molar HCl, using both an indicator and a pH meter. The value of Ka for the sorbic acid is 1.7 times 10 to the negative fifth. Fantastic. So this is actually going to be the titration of a strong acid and its conjugate base. So they're kind of telling me that sorbic acid is a weak acid. I'm using potassium sorbate, C6H7O2 minus 1, where the potassium would be a spectator ion, but I've got the conjugate base. So I'm titrating a strong acid and a weak conjugate base. The pH at the equivalence point is about 2.54. Which of the following indicators would be the best choice in indicating the end point? If you're just titrating with an indicator, you'd maybe try to stop your titration at the end point, which is the same as the equivalence point. It's one of the most important points in the titration, where we'd have equal moles of acid and base. Now this does make sense then that the pH at the equivalence point is still pretty acidic, because I've got strong acid and weak conjugate base. So I've got, a couple indicators to choose from, and they give me the pKa. It's the pKa of the indicator. Acid-base indicators are just weak acids and bases, and they have Kas and Kbs, and they turn colors when the pH of the solution equals the pKa of the indicator. So if I want an indicator that's going to turn colors at about a pH of 2.5-ish, I'm going to use that thymal blue. These are the pH ranges where they'll turn colors. They'll turn colors when the pH of the solution equals the pKa of the indicator. And so, yeah, we have to pick an appropriate indicator to signal the endpoint if we're not going to graph it. So if I had maybe like a strong acid and a strong base, I would choose bromothiamyl blue. That one's going to turn colors around a pH of 7. Yeah, that would make sense. In a strong acid, strong base, at the equivalence point, it should be neutral. If I use phenolphthalein, maybe that would be a better choice for a strong base and a weak acid, where the pH at the equivalence point might still be a little bit basic. Here I want the thionyl blue. Then I'm going to calculate the pH at the half equivalence point, which is really the only time I use my calculator in the second free response. At the halfway point, we've got that 1-to-1 ratio buffer where the pH equals the pKa. So all I got to do is take the opposite log of the Ka. So I should be looking at about a 4.77. Then, this one, there's a lot that we're looking for. We want to try to sketch this graph. The initial pH is plotted for us, which makes sense. And we're going to put our pH probe in this kind of mildly basic solution, the weak conjugate base. pH is a little less than 10. And they also mark in the pH at the equivalence point, which is a little bit more than 2. And they told me that. The pH at the equivalence point was like a 2.5 or something, 2.54. I got to fill in the rest of this curve. All right, so at the equivalence point, that's where I'm going to see that big jump in pH. This time it's going to be a big jump lower. I've gone beyond the equivalence point, and there's excess acid, so the pH is going to drop substantially around the equivalence point. So I'm going to start at a pH of 10. As I add the HCl, the pH is going to start going down a little bit. And then there's that buffer region where the graph kind of flattens out a little bit. Maybe mine's a little bit extreme. And then it's going to drop dramatically around the equivalence point. Now, they wanted me to mark an X at the half equivalence point. Well, when they had the equivalence point marked in, it was around 30 milliliters. So I'm looking for my half equivalence, or my halfway point, to be around 15 milliliters. And I should be marking that around a pH of 4.77. So we're looking for the right pH at the halfway point. We're looking for the right volume, that we should have indicated the halfway point around 15 milliliters. And then we're looking for like the right general shape of the graph. That here when I titrate a strong acid with that original weak base, the pH should be dropping. And then the last two. The pH of the soft drink is 3.37 after the addition of the potassium sorbate. Which species? The sorbic acid or the conjugate base? The sorbate ion has a greater concentration. And so a couple ways we can think of this. At the halfway point, I would have had that 1-to-1 ratio, and the pH is 4.77. But in this case, the pH here at this point where I'm adding the acid and base, at this point the pH is a little bit lower. And so if the pH is lower, then the concentration of the acid must be a little bit higher. Must be more acid than base. And then finally the last one, a student claims that if potassium citrate is titrated with the HCl, a different indicator should be used. Citric acid has a Ka of about 1.8 times 10 to the negative fifth. Do you agree or disagree? So when we use an indicator, we're trying to indicate the equivalence point, the point where I'd have equal moles of acid and base. In this case, the Ka values of the sorbic acid and the citric acid are really similar. I mean, if the Kas are similar, the Kbs are also going to be similar for the sorbate ion and the citrate ion, which really means then that both of those acids dissociate to about the same extent. So once I hit the point in my balanced equation, I'm going to have equal moles of acid and base. If the acid ionizes to about the same extent, if both acids ionize to the same extent, there's going to be about the same amount of hydrogen produced. And so really then the pH should be about the same at the equivalence point. And in that case, then the same indicator should be appropriate. So in this case, I would say that I disagree with the student's claim. I would not need a different indicator because they're both going to ionize about the same extent. Same amount of hydrogen is produced at the equivalence point. The pH should be about the same.